Electric motors change electrical energy into mechanical energy that's used to drive compressors, blowers, fans, and pumps. There are many different types of motors, but the one thing they all have in common is magnetism. In this segment, we'll discuss the basics of magnetism, as well as a number of motors that have different configurations and starting configurations. Magnetism is a physical phenomenon that's demonstrated by the attraction of an object to iron. The needle on a compass points north because of the magnetic field created by the Earth. This horseshoe magnet is able to pick up small iron objects because of the field generated in the magnet. All magnets have two poles, a north pole and a south pole. Like poles of magnets repel each other, while opposite poles attract each other. This attraction and repulsion is called magnetic flux and is often referred to as the magnetic field. A weak magnet will generate a weak magnetic field, while a stronger magnet will generate a stronger magnetic field. Permanent magnets, like the ones we just saw, can remain magnetized for a reasonable period of time, while electromagnets are created with the aid of flowing electric current. As current flows through a conductor, a magnetic field is generated. More current flow will result in a stronger magnetic field. Creating coils of a conductor can also increase the strength of the magnetic field and can be used to open and close sets of electrical contacts, such as in the case of the relay or contactor. Electric motors rely on the forces generated by magnetism in order to create the rotating motion that performs a wide range of tasks in the heating, cooling, and refrigeration industry. In an electric motor, the magnetic forces of repulsion and attraction cause the motor to turn. To illustrate the basic operation of an electric motor, a bar magnet is suspended within the magnetic field of a horseshoe magnet. The horseshoe magnet does not move and is called the stator, or stationary part of the motor. The bar magnet, positioned in the magnetic field of the horseshoe magnet, has the ability to rotate and represents the rotor, or the portion of the motor that turns. Since like poles repel each other, the bar magnet will rotate until the north pole of the bar magnet is lined up with the south pole of the horseshoe magnet. Once the opposite poles line up with each other, the magnetic attraction between the opposite poles will cause the bar magnet to stop. In order for the bar magnet to continue to turn, the poles of the horseshoe magnet must change. This will cause the bar magnet to turn another 180 degrees. To keep the bar magnet turning continually, the horseshoe magnet must constantly change its pole configuration. This is the same concept on which the electric motor is based. At the beginning of a cycle, the poles of the stator would be configured as shown here, and the rotor will turn so that its north pole aligns itself with the south pole of the stator. During the second half of the cycle, the polarity of the stator poles is once again reversed, causing the rotor to turn so its north pole is once again aligned with the stator's south pole. The polarity of the stator poles continues to change, causing the rotor to turn as long as the motor is properly energized. The shaft of the motor is connected directly to the rotor, enabling the motor to do useful work, such as moving air, water, or refrigerant through heating, cooling, and refrigeration equipment. The speed at which a motor operates is determined by the number of poles it has. The more poles a motor has, the slower its operating speed will be. This formula determines motor speed based on the number of poles. A 4-pole motor will therefore have a calculated speed of 1,800 revolutions per minute. Next, we'll examine a number of motors that have different running and starting characteristics and perform a number of different tasks in our industry. The shaded pole motor is intended for use when the application does not require large amounts of starting or running torque. These motors are commonly used to operate small fans that are connected directly to the motor shaft. In order for the motor to start turning, starting torque or a twisting force is required. In the shaded pole motor, this starting torque is provided by heavy copper bands that are wrapped around a portion of the stator winding. When the motor is energized, a magnetic field is produced by both the shaded poles and the main winding. These fields are out of phase with each other, causing the twisting force that is needed to start the motor. A single-speed shaded pole motor has only one winding and can operate only at one speed. Multi-speed shaded pole motors have a number of power leads that, when connected to a power source, will enable the motor to operate at different speeds. The speed of most multi-speed shaded pole motors is controlled by adding resistance to the motor. When operating at high speed, the run winding is smaller, providing less circuit resistance. Low speed, on the other hand, introduces more run winding resistance to the circuit, causing the motor to operate at a lower speed. The split-phase motor utilizes a phase shift in the magnetic field to create the required starting torque. This type of motor is used for heavier applications because of its higher starting torque. Instead of the shaded poles, a separate start winding is used to create the needed torque. The run winding is energized whenever the motor is energized and keeps it operating as long as power is supplied to the motor. The start winding is a higher resistance coil that is only energized long enough to get the motor started. The start winding is removed from the active circuit by a device such as a centrifugal switch, which opens and closes its contacts based on the speed of the motor. The difference in the resistance between the two windings creates magnetic fields of different strengths, generating the needed starting torque for the motor. Once the motor reaches a speed within 75% of its running speed, the centrifugal switch opens, de-energizing the start winding. The motor will continue to operate with only the run winding energized. Once the motor is de-energized, the contacts on the centrifugal switch will close in preparation for the next start. Split-phase motors that require more starting torque often utilize capacitors, which are electron storing devices. Capacitors can be used to increase the starting torque of a motor or to increase its running efficiency, and are rated in microfarads, which indicate the strength of a capacitor. Capacitors are constructed of two aluminum plates separated by an insulator. The electrical symbol for the capacitor indicates the plates. Starting capacitors are designed to be in the active electrical circuit only during motor startup. Because they're only in a circuit for a short period of time, they do not generate a large amount of heat and are enclosed in a bake-like or plastic canister. Starting capacitors are commonly available in the 75 to 600 microfarad range. Run capacitors, on the other hand, are designed to be in the active circuit whenever the motor is energized. These capacitors are oil-filled and are encased in metal shells. Run capacitors are available in the 2 to 60 microfarad range. Some newer run capacitors that are found on smaller applications, however, are not filled with oil. The capacitor start induction run motor is very similar to the basic split-phase motor that was discussed earlier in this video. The main difference between the two is the addition of the starting capacitor. The starting capacitor is wired in series with the start winding. Once the motor reaches 75% of its operating speed, the centrifugal switch opens, de-energizing the start winding and start capacitor. Another type of motor commonly found in the HVAC industry is the permanent split capacitor, or PSC motor. These motors have good running efficiency and have a moderate amount of starting torque. The PSC motor does not use a starting capacitor as in the capacitor start motors just discussed, but instead uses a run capacitor. The run capacitor is connected in series with the start winding and is in the active circuit whenever the motor is energized. Both windings are connected to a common terminal labeled C in the diagram, which in turn is connected to L2. From the common terminal, current will flow through both the start and run windings. After the current flows through the run winding, it flows back to L1. The simple PSC motor that is shown in this figure has one start winding and one run winding, and it's designed to operate at a single speed. PSC motors that are designed to operate at different speeds are manufactured with additional run windings. The speed of the motor is determined by the external run winding connection. The capacitor start, capacitor run, or CSR motor is the best all-around motor used in our industry. It utilizes a running capacitor to achieve the good running efficiency of a PSC motor and a starting capacitor to give it a high starting torque. These two capacitors are connected in parallel, and the effective capacitance will be the sum of the capacitors. For example, if the starting and running capacitors have ratings of 100 microfarads and 10 microfarads, the total capacitance in the circuit will be 110 microfarads. In order to remove the starting capacitor from the circuit, there must be a set of electrical contacts in series with it. These contacts will open when the starting capacitor is to be removed from the circuit. If a current relay is used, remember that the contacts are normally in the open position. This set of contacts is controlled by a high-resistance coil that's wired in parallel with the start winding. This coil senses the induced voltage in the start winding and causes the normally closed contacts to open at the appropriate time. The coil and the normally closed contacts comprise a device known as a potential relay. When the motor is initially energized, both the starting and running capacitors are in the active circuit. Once the motor reaches its designed operating conditions, the starting capacitor is removed from the circuit, leaving the motor to operate as a PSC motor. The three-phase motor is by far the most powerful of all the motor types discussed here. These motors have an extremely high starting torque and do not require the use of capacitors. Three-phase motors require three-phase power supply, which feeds 3 hot legs to the motor. Each of these 3 phases is 120 electrical degrees out of phase with the next, creating a very high starting torque and a high running efficiency. Many three-phase motors are designed to operate at different voltages to satisfy different system requirements. Three-phase motors can be internally wired as either a star or delta configuration. The star configuration is often called a Y configuration. A motor that's configured as a star will have a schematic similar to the one shown here, and is field wired according to the voltage that will be supplied to the motor. The high voltage connection configures the motor windings in the shape of a large Y. Power is supplied to wire leads T1, T2, and T3. When the motor is to be used at the lower of the 2 voltage ratings, the windings are connected to form 2 smaller Ys, which are wired in parallel with each other. L1 is connected to both T1 and T7, L2 to T2 and T8, and L3 to T3 and T9. The delta configuration can also be used at either voltage rating. When used at the higher rated voltage, the motor is field wired so that the windings resemble a large triangle. T6 is connected to T9, T4 to T7, and T5 to T8. Power is supplied to the motor through T1, T2, and T3. At the lower voltage, the windings are configured as two smaller triangles wired in parallel with each other. Hermetic compressors are designed for single and three-phase applications and are becoming very popular because of their low cost. Single-phase compressor motors can be of the split phase, capacitor start, permanent split capacitor, or capacitor start, capacitor run variety, depending on the required application. The motors inside these compressor shells are surrounded by both refrigerant and oil, so it's important that there's no electrical sparking inside the compressor. Sparking can cause a short circuit, as well as refrigerant contamination. For these reasons, any and all starting components are located outside the compressor shell. All single-phase compressors have a start winding to start the motor and another to keep the motor running. In addition, there are 3 electrical terminals used to supply power to the motor. These terminals are labeled C, S, and R, which stand for common, start, and run. The run winding is connected internally between the R and C terminals, and the start winding is connected between the S and C terminals. The technician can easily determine which terminal is which with the help of an ohm meter. The first step in determining the identity of the terminals is to assign a temporary name for each terminal, such as A, B, and C. Next, take a resistance reading between each set of terminals. Let's assume that the reading between terminals A and B is 12 ohms. The reading between A and C is 2 ohms. And the reading between B and C is 10 ohms. The largest reading was found between terminals A and B. The remaining terminal will be the common terminal. In this case, it's the C terminal. The larger reading between C and the other 2 terminals identifies the start winding. In this case, the larger reading is 10, which is between C and B. This makes terminal B the start terminal. The remaining terminal is the run terminal. The run winding has a resistance of 2 ohms and the start winding has a resistance of 10 ohms. 3-phase motor windings, on the other hand, are all the same, so taking resistance readings is not necessary. Besides, they don't use starting components anyway, which makes them very easy to field wire. Magnetism is the phenomenon exhibited by the attraction of an object to iron. The magnetic forces of repulsion and attraction cause motors to turn. Shaded pole motors rely on heavy copper bands to provide starting torque. Split-phase motors are designed with a separate start winding to produce the starting torque. The start winding is only in a circuit long enough to aid in motor starting. Some motors use starting capacitors to increase the amount of starting torque. Permanent split capacitor, or PSC motors, use a running capacitor to improve its running efficiency by keeping the start winding in the circuit. Some motors use both a running and starting capacitor. 3-phase motors have an extremely high starting torque and excellent running efficiency. Motors found in hermetic compressors can be split-phase, capacitor start, capacitor run, or 3-phase. Using an ohm meter to take resistance readings of the windings can identify the terminals on a single-phase hermetic compressor. This series continues in segment 8 on components of electric motors.